Yeah, what's nice about this setup, is that, again, same configuration where I was running the amplifier in the previous video, but it's actually pretty easy because I've got, these different scopes. And again, with this, I'm using it as an amplifier, but I can also very easily change over to looking at its transconductance curve, just by simply going to the right scope, hitting run all, right? And we don't want to run this because that's garbage. But go to this scope here and hit run, and guess what? Now we're back to seeing the transconductance curve. So let me set that back up. So, that makes it easy to go, back and forth. So if I wanted to go back to the amplifier version, let's go over here and hit run, and go back over here and hit run all. And now we're back to it being an amplifier. So again, if I wanted to measure, one of the family curves, to get back to that mode, I'd have to move my scope probe from here to this resistor here. Oops, which is hard to grab onto. Okay, and that gives you that fucked up waveform. But you can go back to the appropriate earlier wave gen, and watch this not work, and then go back to, I think it was this scope here. Yeah, shit. So now we're back to our parameter. Just, I wish you could name these waveforms. Well, let me take this out. Window button here to detach it and take it over here so you can see where the scope went. Okay, that's the active one. And I can go, vary the parameter, and I got persistence mode turned on still, so let me turn that off. But we're back to being able to see one of the family curve test set. So I can go, between these three different tests, with relative ease, and then, I still got the results of the previous one. That's not good. Um, but here's the transconductance curve, so I got that available, and that never really changes. But, one of the things you would have difficulty estimating, by the way, is what the actual transconductance is, because the transconductance technically is the derivative of this curve, which you mostly see in textbooks. But, if you got these two parameters, what IDSS is, its maximum current, with about 5 milliamps, and its pinch-off voltage, um, is just under 2 volts, you can put those into the curve and maybe, estimate the transconductance. But it's actually the derivative, if you had a curve tracer, that, could actually make a tangent line on this curve, you could estimate what the transconductance actually is. And transconductance, a great way of understanding its basics is this. And I learned this off Elliott Sound Products, and it's actually in, most textbooks. But, this book's by, from 1992. It's, from Hazen, which this is the only edition they put out of this book. But it's actually really good for bipolar transistors. It's a really excellent bipolar transistor book. Um, but um, there are other books out there that are probably better at covering FETs, because he only spends like 55 pages on both JFETs and MOSFETs in this entire book. Unbelievable. But at any rate, like I said, if you got a millisiemens, millisiemens, it's pretty much, like they're talking about here, it's 1350 microsiemens. Well, that actually works out, to 1.35 milliamps per volt. So you can kind of get that, idea that, that's a good way of looking at millisiemens. The transconductance figure is, you know, is, you know, a certain amount of current per volt, because that's what it is. It's a voltage to current amplifier. That's transconductance. But this, you know, kind of helps materialize this, you know, this microsiemen, millisiemen bullshit, you know, in that, you know, it really is, you know, just an interesting way of looking at it, to say, you know, that basically for every volt you'd have 1.35, you know, milliamps change, you know, for every 1 volt of input. Or if you're doing a fractional volt, you know, like they're talking about here, you'd end up with, you know, a fraction of that. You know, like they say, you know, for a zero point 0.2 volt change, you know, they see 0.27 milliamps change in current. You know, that's how they were estimating it based on, you know, one of these curves here. So that's what's kind of neat about this book. You know, it does have a lot of curves like this in it. You know, that shows both of these side by side, because both of these are actually very useful curves. And of course, I can't generate this because the voltage doesn't go high enough on this analog discovery, especially to do sweeps on the drain source voltage, etc. But at any rate, you know, it's just, you know, it's a convenient arrangement. So if you got yourself an analog discovery and you want to test JFETs, you know, since its transistor tester doesn't have that built into it, you know, it's a way you can go about it. But again, you try to have to estimate it kind of the same way he was doing there. But you know, it sucks that you don't have cursors here, so I can't get a direct reading on this. You know what this corresponds to. So I mean, I guess that's, you know, like half a volt there and minus 1 volt, so it's about 0.5 volts change. Um, you know, for, you know, 3 milliamps to, you know, like 1.5 milliamps change. So that's about, you know, 1.5 milliamps for a half a volt change. So that'd be 3 milliamps per volt. You know, so that, in other words, this is 3 millisiemens approximately. Um, but I was gonna fuck around, and this is why I was gonna do, and that's why I wanted to make this video before I moved on. I was gonna try to take this thing here, you know, this amplifier, and see if I can, you know, trick it into, you know, doing a gain calculation, you know, that puts it in transconductance, because, you know, it has a network analyzer, but again, it's not going to be able to do that. It's looking at voltage for in versus voltage out and everything else, and doing a frequency sweep. That's not what I'm interested in. I'd be interested to see if I could do a measurement, though, that takes the voltage peak to peak of the current waveform and, you know, the voltage input waveform, and to see if it can generate a transconductance estimate based on the amplifier screen here, because I might be able to do that. Since again, there's no good way I can do that directly off any of you know, these other measurements. So, but let me try that, and I'll get back to you in a sec. Alright, so trying to continue the video, I'm trying to experiment with a camera holder so everybody can see it. I don't think you can see the damn thing. I'm going to have to hold it for now. I was trying to use my little arms of death here. But, yeah, you can see right there, you know, basically in that same amplifier deal, you know, I set up some measurements, you know, measuring the peak to peak at channel 1 and channel 2 for shits and giggles, but it's really the math channel that's important. That's in milliamps and that's in volts, right? And I went in and recreated a script, you know, when I was experimenting with amplifier gain, and that looks like it works. I'm interested to try that out when I get an actual voltage amplifier. And this is a built-in default little function, because basically to add a measurement, if you don't know, you know, they got defined measurements, but you got to pick them for every channel. So, you know, but for a given channel, you know, they've got a bunch of vertical and horizontal measurements. So, you know, I could add, for example, you know, like frequency, all right, and see, frequency pops up there. Um, but you know, you can do kind of custom, but the problem with custom is you're kind of limited to that very channel. It won't let you work outside of that scope. So, but you know, you got the same functions. Thank God for a math channel. But if you want to add something that actually deals with more than one channel, like I have here, you got to actually, go hit add. All right, but they got custom global. All right, so that global allows you to actually do a global formula like this one that's pops up with this basic phase calculator. So that's what that is right there. That's this program running. But anyway, I kind of took that and modified it for shits and giggles, and you know, hell, I forgot to name it properly. Let's see. Yeah, okay. Well, I gotta change the name here. So let me do that real quick. Anyways, I'll call it TransCon, for transconductance. Um, Let me save it. Damn, I guess it's a new name. Transconductance. Then I hate. Why do these damn things always put the damn extensions there? That just always gets in the way. There's no reason to do that. The extension to the file is clearly there. Heck, almost every program does that. You do not. It's redundant to have a stupid, extension in this fucking name window. Anyway, okay. So let me go ahead and change that. Okay, now that says, TransCon, and let me change the cursor so you can see it. So I got it in millisiemens, and you can see, the formula I used. I basically commented out most of their code. It's got a bunch of junk in there. I thought I might want to use it as a reference. This thing does actually have code completion on it, which is pretty cool. So, I guess you can start typing something on there. I don't know if it pops up or not. See, this control space or something. Yeah, there you go. So it does have code completion on that, so that's actually kind of cool. But I hope I didn't just fuck it up. But yeah, this is the formula, I used. Let me spread this out here. It'll be a little easier to read. This is from a script I wrote in the script editor um, earlier, a few days ago. But anyway, it shows you, what I used, to calculate it just crudely. Hopefully there's a more efficient way of going about this. But again, I'm still learning this whole tool in general. So, but at any rate, this gives you, what you need to do, and I basically multiply my thing by 1,000, so it reads out in millisiemens, because you can just enter your own unit in here, so you can just type it in, or you can, select a predefined unit, but you can just type it in. So that was at least smart of them. But at any rate, let me cancel that. But yeah, that should be a because that's about where I figured it'd be, based on the calculation I did earlier, as you saw, I said it'd be maybe 3 millisiemens or so, and, running this amplifier at about that same, probably in that same area, shit, I don't know. But anyway, it's coming out to theoretically 3 millisiemens. I don't know how accurate this is, haven't really tested it, because again, this thing is so confusing to work with, because I should be able to just enter what the peak voltage is and what the negative peak voltage is, and put whatever value in there I want, and have it figure out where to position offsets and all that crap. I mean, really, I shouldn't even mess with offsets unless you're, I mean, in this case, it would make sense. But still, if I just entered a negative, like 0 is my peak voltage and -3 is my minimum voltage, I'd never have to worry about blowing my frickin' transistor out, because this thing will start applying a positive base to it. The only time you can get it to actually do something is if you hit run, so you can't even start adjusting it until the thing's actually running and your transistor's in smoking ruins. I mean, it's just baffling. But at any rate, this is, a quirk of the damn tool that shouldn't be here, because it's a software issue, and this is open source software, and I get really aggravated because it is open source, but I have no intention of spending 6 months trying to figure out how to even compile their damn program, let alone figure out what the hell they did so I can make my own modifications. So it's way easier for me, way less time, just to make my own device. my own transistor tester. I don't need something this fancy to test transistors. But anyway, so I don't know how accurate this is. Maybe I'll find out as time goes on. But anyway, I just wanted to kind of show a few extra things before I actually do move on, because I'm going to move on and maybe do something like this, an actual amplifier. Um, using the data I have, because I'm going to need the data I have, from these. I guess I fucked that one up good, didn't I? But certainly using this, and I can set that other thing back up. But at least I showed there is a way, hypothetically, and that's the value of this end of this video, of measuring the actual transconductance. Even though you would have to dick with things, and I'm still not quite sure. Again, because this thing gets confusing, and you don't want to enter the wrong value. I mean, it's like I said, in theory. Just remember that negative 352 millivolts. So let's see what happens when I change that. Okay, see, that's making my waveform go into the positive area, so you don't want to do that. Yeah, the transconductance is remaining fairly uniform, so interestingly. Um, Again, I don't know if that's appropriate or not. I'm not really sure because I'm so confused by my tools here. You should never have tools that fight you. Let's see. Remember, so minus 352, right? Let me set that back to what it was. Okay. So now let me try varying the offset. Minus 565. Hey, I can vary the frickin' the symmetry there. I got an old function generator where you can do that same thing with, from Tenma back 30 years ago. Jittery though, so it's hard to use at this point in time. Okay, but let me try to see if I can 565, and let's see if oh, good, look what's happening. Our transconductance is changing now. So down to 2, down to 1. As I vary this, and we're still definitely in the negative voltage territory, so those are still appropriate signals. But so yeah, I mean, it appears to be, because that's what I expect. The transconductance should change, based on where you're at on this curve, where your Q point is and amplitude and everything like that. That's what I'd expect to see. Your transconductance is going to be different here than it is here, and even slightly different there. So yeah, and transconductance supposedly gets lower here. It's a lower slope. Smaller change of current with respect to voltage. So you expect the transconductance to change as you move closer to a negative operating point. So you might even be able to see it more clearly if I was changing other things. But yeah, you can see our transconductance is actually below 1 now, and I'll raise it up, as I continue to raise this offset here, we'll get, we're getting kind of close to going positive though, but transconductance is 3.3, we're still just barely negative, and at 417 millivolts negative offset, but we're at 3.4 on I think it was, what was it, 565 I started with? So, yeah, 3.3. So, anyway, so it's pretty cool. I mean, it looks like it's actually plausible that it's working. Again, these things still just confuse the shit out of me because you just not having direct control over everything. It's irritating. Anyway, that's enough for this video. Cheers.